In this video, we'll talk about the idea of applying a function to a sequence, what that means, and how it behaves, provided you have a nice enough function to deal with. So the point is you can also do this, right? You can also apply a function to a sequence and see what you get out of it. The basic idea is sort of the following. If I have a sequence an, right, say, just for sake of illustration, that an is n squared minus 3n. That's a sequence. It's fairly well behaved, but it's a nice sequence. If I have the function f of x is sine of x, I can think about evaluating f on this sequence. So I can look at the values of f of an, which would be sine of n squared minus 3n, and this gives me another sequence. So we have a new sequence, the sequence f of an, which is exactly the one we have defined up here. Now the question is, how does the limit of an relate to the limit of f of an? That'd be a really nice thing to know so I don't have to handle this new sequence completely separately. You'll see this come up a lot in different problems you try to solve where you don't just have n squared. You've got things like e to the n squared. You don't just have 3 minus 1 over n. You have e to the sine of 3 minus 1 over n. You have all these things nested together. And you want to know, can I just do this in an easier way? And the answer is yes. So the statement we have here is the following. So if the function f is continuous, and we have the limit as n goes to infinity of an existing and being some L, then the limit as n goes to infinity of f of an is just f of L. Basically, since f is continuous, I can put the limit inside the function here to get this should be f of the limit as n goes to infinity of an, which is f of L, because the limit inside is L. So provided I have a continuous function, I am allowed to just move the limits around and take limits inside and apply things to that. This makes these sorts of processes a lot easier when you're trying to solve for these limits if you can just move them around because the functions are all continuous. This is again why continuity was super important back in Calc 1 and is still very important now, is it allows us to do these sorts of things and make our lives easier. Instead of having to solve every single one out individually, we can sort of do them all at once and make the process easier by knowing these facts. So here's a quick example of that. For f of x equals e to the x, and an is sine of n over n squared. What is this limit here? This question could also just be written out directly as what is the limit as n goes to infinity of e to the sine of n over n squared. Right, that's what basically this is asking you, is exactly that question there, broken into a different way. So, assuming our limits all exist here, I know that by the statement above, this is f of L, or e to the L, for L being the limit as n goes to infinity of an, which is the limit as n goes to infinity of sine of n over n squared. Now, how do we find this L, and does this L exist? Well, it turns out the idea here is the same as the one we had last time. This is a squeeze theorem problem because I have a sine n again. Just like for functions, seeing things that oscillate should let you know this is probably a squeeze theorem type of approach. So, because negative 1 over n squared is less than equal to sine of n over n squared is less equal to 1 over n squared, and both of these go to 0 as n goes to infinity because they're normal functions, 1 over x squared and negative 1 over x squared both go to 0, the squeeze theorem tells us that this also goes to 0. Thus, our L here is 0, so the limit we want is e to the 0, which is 1. So while it may have looked really complicated to figure out this limit at first, if you're just staring at this function here, once you break it down into pieces, it becomes a lot easier to sort out what's going on. And the main thing is this limit must exist before you can apply this sort of thing. So I can't just do the sine one directly because that one doesn't exist. I have to use a squeeze theorem to prove it exists, and then I can go forward from there. That's the idea of applying limit to function. The basic idea is I can break things down to make it easier for me if I have a nice function to work with at that point. You should consider doing this whenever a problem presents itself in a way where you have sort of complicated limits to take, break it down into pieces, and use the function notation to make it easier to figure out what those limits are.